Hello, everyone. This is Professor Ma, and this is the sections on divergence theorems. Okay, we start out with where we left out last time. Let's review the flux integral, which is this. So I have these things called the flux integral. This, of course, it's a limit of a Riemann sum, and we're summing over these, where each of these terms is roughly the volume of the flow F. F, of course, is a flow field across small patch of surface. And what is N? N is the unit normal fields to the surface. And so here is a picture for the things. Let's put all the players here. We have the surface sigma. Okay, and we have on this surface, we have a flow, capital F, which is a three-dimensional flow. This flow is going to be the vector field, 3D vector field. Okay, and at a point, we have the normal fields to the surface, which are drawn in this black perpendicular vectors of length 1, unit normal fields. Okay, and now let's see what these things is. Okay, so first of all, we take the domain, we cut into little rectangles, and then we look at one particular rectangle and corner at xi, yi, and so I look up and see where the z, the output is on the surface, and there they are. Let's notice in these particular pictures, we have that, if I blow it out a little bit, we have these 3 points, which the 3 red dots actually are points on the surface. But the 4th point or the corner of that blue dot, okay, and its point, it's on the surface, but it might not sit on the plane where these 3 red dots are. Okay, I just want to point that out. Because next, what we're going to do, we're going to find the tangent plane. We're going to replace the tangent plane at the point xi, yi to the surface. We're going to treat that little patch of surface that before, let me erase this little patch of surface that is four points cuts out on the surface. We're going to replace that patch by a little tiles that's from the tangent plane at the point xi, y. So if I blow this point up and look at what's happening at the point, okay, I'll put points on the other corners. Okay, so below we have the surface, okay, underneath this plane, and then what is the formula? Fi dot ni, and Fi dot ni, of course, is the length of the projections, since n is the normal, unit normal. Okay, so it's also the shadow, and the shadow is going to be the height of the portion of the plane that's going to be float across the space. Okay, we're going to, therefore, we approximate the surface, the flow through that little patch is approximately this dot product times the area of the surface, ds. Okay, and of course, we'll cut them into down I goes from 1 to infinity, then we'll let I, in particular delta si go to 0, and these converge into these symbols of the diverging or the flux integral. Okay, and so these volumes of the parallel pipe, okay, are squashed box is approximate volume of the fluid flowed across the patch of surface. Okay, and that's what the flux integral is. Okay, and of course, when we calculate, we have to convert for the ds when we convert it into the double integral over the domain D, we convert this into this integrand times dA. Okay, we call this integral current of dA, and so we just convert that into the calculation part. Okay. And D, of course, is the domain where the surface sits on top of. Okay. Now, what's divergence theorem? Okay. First, what's a divergence? So in three-dimensional space, we have this flow capital F, and the divergence, and of course, it is given in vector form, has x component as some function f, y component some function g, and then z component some function h. Okay, and I take for the x component, I take the derivative with respect to the x component, take derivative with respect to y component, take derivative with respect to z component, the partial derivatives, and add them together. Okay. In a sense, f of x is to rate the flow across the change in the x directions. Okay, then you calculate the rate of flow changing the y directions. Then finally you calculate the rate in the z directions. Okay, then you cannot total the number. You get one single numbers, and basically when the number is positive, it means there are things that is flowing out more than flow out more than the things coming in, flowing into it. When this number is negative, it means that more things is flowing into it than is flowing out. Okay. And when it's zero, means the two balances out. Okay, so that's a divergence. It's a function. Okay, it's a function x, y, z, and the divergence converts calculating the flux, the flux integral, the flow across the surface, remember? But in this case, the surface is the surface of a solid, a nice solid, okay? We just leave it there, but most of the things we work with are nice, okay? And all of the things that we're gonna work with are nice, okay? So for instance, spheres are nice, okay? Anything you can think of are nice, basically. Anything you can draw, basically, are nice. Okay, for instance, here's like they have a vector field that's flowing out this solid. The solid is G, and the surface is sigma, and then the flux integral is these, and divergence theorem says, oh, this flux integral you can convert into a triple integral of these divergence of these functions in x, y, z. Kind of look at density functions now. And that actually, if you calculate this total, this quote unquote mass, that's the same as the total flux outward. And this convert a surface integral into a triple integral. Okay, let's look at some examples. Okay, let's very simple example. Okay. We have a constant flow, 1K, so it points upward, and we want to calculate the total outward flow across the surface of the unit cube. I'm going to set the unit cube at 0, 0, 0, okay, and x1, z1, 1. And so basically the ends are the outward normal, and the flow is upward directions, 0, 0, 1, okay. And we're going to calculate two ways. Once calculate the total flow by calculate how much it flow across each surface is a surface integral, the flux across each surface. Then we're going to second one, we're going to use divergence integral. Okay, and the answers is very simple. Okay, and for the flowing across the surfaces. Since the flows upward, so anything point to the sideway, the x and y directions, those the normal are perpendicular to the blue line. The green one are perpendicular to the blue line. So there, F dot M is going to be 0. So the flowing across the wall is 0. And now flow upward across the top is equal to 1, and the dot product's 1s. And flowing downward, flowing down, okay, it's -1. Okay, the surface is -1, and data with the flow 0, 0, 1 is -1. So therefore, the total flow across all 6 surfaces is 0, which makes sense. Basically, it tells you nothing flows, the volume doesn't change not the volume, but the amount of flows into this cube. Okay, in and out are the same. But divergence theorem says, let me take the derivatives of these partial f x plus partial gy plus partial z hz, and since this case is a constant, so the divergence 0, and I'm integrating this 0 over the globe, and then divergence 0. So this is the simplest case verifying that, that this actually works for the cube, simplest case. Okay, here's another example. Outward flow on the globe, on a sphere of radius r. Okay, so this is a sphere of radius r over here, if you like. And it flows out, and calculate the total flux across the surface, the flow. The divergence of these partial derivative x1, partial y1, partial z1, so altogether 3. So I can integrate 3 over this solid. So this is the divergence. And the theorem says the total outflow, our outflow is the integral of the divergence. Okay, and so the flux integral is equal to integrating the constant function 3 over the globe, and of course the globe has basic 3 times the volume of the spheres, and it's 4/3 pi r cubed, and it's cancel the 3, we get 4 pi r cubed. Okay, and if we think about it, this is what we expect, because the surface area of the spheres of radius r is 4 pi r squared. And this flow is equal to the radius, it's in the directions, and the length, the rate of this, the length of the flow is equal to r, is equal to the radius of the sphere. Okay, so at each point, the flow across the point outward perpendicularly at r, whatever r cubic r cubic centimeters per second, whatever unit is. Okay, since the total surface is 4 pi r squared, so times the rate of flow r is 4 pi r cubed. Okay, this is what we expected, sort of. If a surface flows in the normal directions at a constant rate, then the total flow is going to be the rate times the surface area. Okay. And here is a problem to find divergence of our flux, okay, over cylinder. Okay. And calculate the divergence. And now I want to integrate this divergence x squared plus y squared over the solid G. Okay. And we change now. Oh, by the way, what does this look like? This is a cylinder, x squared y squared equal to 1. Should I draw this? Okay, so it's going to be a cylinder sits over Okay. And we're going to do it from where? Between z equal to 0 to z equal to 3. Okay. And these, of course, goes in the back over there. So we have this cylinder. Yeah. We'll calculate the total flow out of the cylinder. Well, since we're in these things, we are integrating over this is the solid G, and then now it's convenient to transform these into cylindrical coordinates. Okay, and in this case, x squared plus y squared is going to be r, and so this is r plus 1. Okay, and dv turns into RD theta, and this is over the constraints and over the z r theta z. Okay, and so then just integrate this out, and we get 9 pi over 2. Okay. So this is where we use cylindrical coordinates or spherical coordinates when these type of problems shows up is convenient for the particular shape. Then we use a particular coordinates. Okay, that's it. Bye-bye. Until next time. Bye. Stop.